Hello and welcome back to the lab. So today we're going to use the HP415E SWR meter to actually measure SWR the way the instrument was designed to be used, which we haven't done up until this point. So the way it's designed to be used is using a slotted line. And this is an example of a slotted line. This is a coaxial slotted line, has an end connector on one end. This one has an APC7, a 7 millimeter connector on the other end, um, and a center conductor down through the middle. It's a coaxial piece of transmission line that has a slot in one side, and you use the slot to insert a probe and slide the probe along the length of the transmission line to measure the maximums and minimums of your standing wave, and that from that measurement you can calculate the SWR, or the 415E will actually display the SWR directly. Now, there are various types of slotted lines. This is a coaxial slotted line. This one here is a waveguide slotted line. So there's a waveguide opening on both ends, right? There's no center conductor because it's a waveguide. But again, there's a slot along the side, and the probe slides down. The probe inserts into the slot and makes a measurement of the standing wave that's present inside the section of transmission line. We have one of those slotted lines mounted in here in this slotted line carriage. A slotted line carriage is a way to mount the transmission slotted line and to move your probe along the length of the slot in the slotted line using this rack and pinion type knob, and actually measure the distance that you've moved the slotted line probe using this scale calibrated in centimeters and tenths and 100ths of the vernier on this distance scale. Now the probe that we're using is this, the HP model 444A, and if you look carefully you can see a little point on the tip, and that little point reaches down into the slot in the slotted line to take a sample of your standing wave that's present in the slotted line. It's fastened into the little moving part of the carriage with a little thumb screw. And again, you turn the crank and read the distance along the slotted line off the scale here in the front. In addition, you can add a machinist's dial indicator between these 2 points to get a more precise distance measurement using your dial indicator. I don't have a dial indicator, but we won't be needing that anyway for the frequencies we're looking at. So the input to your RF signal comes in here, AM modulated with a 1 kilohertz sine wave or square wave, AM modulated RF signal at frequencies depending upon what type of slotted line you're using. The slotted line works from 3 to 8 gigahertz or something like that. And your device under test, whether it's a load or an antenna or an input to another device, goes here at the far end, which would be the reference plane or the test plane. This one happens to have a type N connector at both ends, the input side and the output side. And the scale on the carriage measures the distance from that calibration plane from 8 centimeters. We're 8 centimeters away from here to here, all the way down to 19 centimeters. But really, we're just going to measure the distance between 2 points, either a maximum and a minimum, or between 2 minimums or 2 maximums to make our measurement. So we're going to make an SWR measurement. The output of the 444A probe, which has a crystal detector inside of it actually, is the detected AM modulation at 1 kilohertz. Comes out of the BNC connector at the top, and that will go into our 415E. And from that that detected 1 kilohertz sine wave will be the proxy that indicates the relative amplitude of the RF signal inside the slot in the slotted line, as detected by the probe and indicated on the 415E. So before we make some SWR measurements, I thought it would be fun to actually measure the wavelength of our RF signal going in. And once we get a measurement of that, we can compare it to the known frequency of my signal generator to see how accurate our entire test setup is. In order to do that, we want to use a short. This is a calibration short. It's a solid piece of metal. It's an end connector that shorts the output here. When you short the output, or the test plane over here, when you short that, you will get a reflected wave, um, reversed in phase by 180 degrees, and reflection. So your entire incident wave, your entire forward wave, should be reflected in this direction with a short, also with an open. But with a short, you get a very clean, clear indication. Technically and theoretically, this would result in an infinite SWR. A short would result in an infinite SWR. Now, you can't actually measure infinite SWR with this test setup, but it will give us very clear maximums and minimums of our standing wave that's inside the slotted line, transmission line. So what I wanted to do was measure the distance between two of the minimums, and those should occur at every half wavelength. So we'll measure the distance between those two points, and we'll multiply by 2 to get the wavelength of the signal coming in, and then we'll divide that into the speed of light, 3 times 10 to the 8th meters per second, and we'll calculate the frequency and see if it matches the frequency coming in. And if it does, we know our test setup is working properly. Now, before you think that I'm an expert at this, I've only tried this for the very first time a couple days ago, and it seemed to work. I tried it as sort of a dress rehearsal, so I didn't make a fool out of myself on camera. And it seemed to work, so I'm hoping that it works again today. But let's get started with making our measurement of the wavelength and see if that makes a lot of sense. And then we'll go on to measure the SWR of a couple different terminations I have back here. Okay, so I've turned on my 2 signal generators. Here's the 8642B, which works up to 2.1 gigahertz. I've had this one for about 2 or 3 years now, and I use it relatively infrequently because it weighs about 90 pounds, and it's a hernia buster basically. But I will probably use it for this test. And above that, we have the 8672A, which I only received a couple days ago. I just bought this online, and it's got a few cosmetic issues and stuff, but it works. And so we're going to use that for frequencies above 2 gigahertz. This one actually goes from 2 to 18 gigahertz, and we're going to take a look at a 4 gigahertz frequency using this synthesizer. Now, these two guys, I don't know if you can hear the fans on them, but they are blasting like a jet engine. And hopefully the noise cancellation on my microphone wipes some of that out. But I didn't turn them on until now because they were very loud. So we're going to use those as my signal generators. All right, let me move the camera back. Okay, so I have my signal generator turned on, and it's 4 gigahertz plus 10 dBm output, and I have it 100% modulated with a 1 kilohertz audio sine wave, AM modulated. And we have a signal that's coming out of our 444A probe. 1 kilohertz is coming out into the 415E. We've adjusted the range to plus 30 is what was required to get a full scale reading on the 415E. And now I will turn the carriage to slide the probe along the slotted line until I find a minimum on the 415E, and we'll take a measurement of that distance. I will keep reducing the range of the 415E to try to get an on-scale meter reading as I look for a minimum and try to null that signal out. We're going down very, very low. This must be a very deep minimum, and the measurement's getting a little noisy because I'm so deep into the weeds here. But it looks like we are right at the minimum. So what I'm going to do now is take a reading off of the scale of the vernier on the slotted line carriage. And that reading appears to be 12.23 centimeters. So we record that reading. All right, and now we'll go back and move the carriage down until we find the next minimum, the next null, and that should be 1/2 wavelength away from the first one, and that will be able to tell us the indication of where the next minimum is and what the wavelength would be. So we'll continue to increase the gain of the 415E while adjusting our carriage until we find the next null. And again, it's very deep, so our measurements are pretty noisy. But that just means we are doing it correctly, I think. Well, it appears that that null is right about here, and we can take another reading off the vernier of the calibrated scale. And that reading appears to be 15.96 centimeters. So we'll record that reading as well. Okay, so when we do this calculation, 15.96 centimeters minus 12.23 centimeters, the half wavelength is 3.73 centimeters. So the wavelength turns out to be 0.0746 meters. That's multiplied by 100. I mean, divide by 100 to get meters, and then multiply by 2 to get a full wavelength, right? That's how we get the lambda equals 0.0746. Frequency equals speed of light divided by that wavelength. 3 times 10 to the 8th divided by the wavelength in meters gives us 4.021 gigahertz. And of course, the frequency we were using was 4.00 gigahertz. So we are off by 0.5%. And I think that's pretty darn good. Seeing as how I've never done this before, and I don't really know what I'm doing, it works out almost exact. So this slotted line technique with the 415E works out great. All right, so let's make some SWR measurements now that we know that our system is basically working. Okay, so first I wanted to test the SWR of this HP model 908A 50 ohm termination. These are specified to be good to 4 gigahertz. So we're going to test it at 4 gigahertz and see if it really is good. We're going to measure what the SWR actually is of this 50 ohm load at 4 gigahertz. So we're going to connect that to our test port over here. Tighten it down. Let's turn our RF generator on. Okay, we have a meter reading over here. Let's adjust our carriage for a maximum and adjust the gain until we have a 0 or a 1.0 on our SWR scale or a 0 on the dB scale. When we hit our maximum right here, you can see already that the maximum is lower than it was with shorts, which I guess is a good thing, right? The standing wave is much smaller on a 50 ohm termination than it was with a short. Okay, now we've set our 0 at the maximum. We're going to look for a minimum. And in fact, really what I should do is adjust the range to expand. So instead of looking at a 0 to 10 dB, we're looking at a 0 to 2 dB range now to actually find the absolute minimum. And when we do that, we can read the SWR directly off the meter scale. And the SWR indicated here, let me see if I can zoom in the camera in a little bit, is 1.03, 1.035, 1.04. It's a little bit noisy, but it's something around 1.03, 1.04. That's our SWR on the 4 gigahertz 50 ohm termination, the HB908A. Well, I think that's a pretty good SWR. Okay, now I thought I would use the same setup to test the SWR of this little cheapy 50 ohm feed through termination that doesn't even have a brand name or a model number or anything like that. This thing might be good to 100 megahertz or something, but I'm sure it's no good at 4 gigahertz. But we're going to find out just how bad it is at 4 gigahertz. It's a BNC connector on both ends because it's a feed-through termination. So it's used to connect to the input of an oscilloscope or something like that, right? It's a feed-through 50 ohm termination. I'm sure there's just a little 50 ohm resistor in there. We have a BNC to type N adapter. We're going to use that as part of our test setup. We're going to end up testing the SWR of this combination of these two devices, actually. But I'm sure it'll be worse than the 1.04 that we got with the other load that was specified to 4 gigahertz. So let's put this one on. And hopefully, let's turn the RF on. Oh, wow. Yeah, already our maximum is higher than it was with the one that specified to 4 gigahertz. Significantly higher. Let's dial for our maximum and set our reference up here. So now it's set for the maximum of 0 dB or 1.0 SWR. Now we'll look for the minimum of the standing wave. Wow, it's much, much deeper than the 4 gigahertz load was. In fact, it's almost, wow, it goes down almost 20 dB deeper. And we can read the SWR scale off of that right there. I already switched from the 1 to 3 SWR range to the 3 to 10 SWR range. And if we read the scale on that one, we can read our SWR directly, and it appears to be about 8 point something, 8.3, 8.3 to 1, something like that. 8.3 to 1. Instead of 1.04 to 1, we have 8.3 to 1. This is a useless termination at 4 gigahertz, but it wasn't ever designed to be used at 4 gigahertz. So there you go. So that's how you make an SWR measurement with the HP 415E SWR meter. Thanks very much for watching. Please like and subscribe, and stay tuned for more fun. I have a part 3 video coming up where we are going to play around with something that we colloquially call the cookie jar. So stay tuned for the cookie jar. Thanks for watching.